So moving along now, we've defined a relation and we've defined some additional properties that we can place on relations, that we can require relations to have, that are quite common in the set of relations that we're already used to dealing with, like divisibility, subset, element of, less than or equal to. So these are quite common properties. And when we actually have a relation that satisfies all three, namely reflexive, symmetric, and transitive, then we have what's called an equivalence relation. And equivalence relations have nice properties, and equivalence classes come out of that. So let's start off by talking about equivalence relations. So an important type or an important class of relations, those that are similar to equality. And in particular, they're similar to equality, but a little bit looser. So let's take a relation on a set A. We call a relation an equivalence relation when it has reflexive, symmetric, and transitive. And if you think about equality, equality satisfies these three properties. Equality is reflexive, symmetric, and transitive. Now, when we have a relation that satisfies these properties, so for example, we can have has the same parity as, is congruent to, has the same birthday as. Well, we already have played around with this rather a lot. We know that even numbers are similar to other even numbers and odd numbers are similar to other odd numbers. And so has the same parity as turns out to be an equivalence relation. It is like equality, but a bit looser. Similarly, is congruent to, that we played with last lecture, is also similar to equality. When two numbers are congruent to each other, they are similar, but they don't have to be equal. And say same birthday as, you can show has these three conditions. So these are weaker than equality, so you can be equivalent without being equal. So we're sort of abstracting away equality to make it a bit looser and a bit more general. So let's draw some pictures of some things that can go on. So let's consider the set of these numbers from 0 to 10 and consider the relation on those, the equivalence relation, namely congruence modulo 4. And we saw that congruence mod n was an equivalence relation because it's reflexive, symmetric, and transitive. We proved that last lecture. So we can draw a picture of this. So let's do that here. And if we do that, we know that 0 is congruent to 4 and is congruent to 8, which is congruent to 0. These form a neat little connected clique here. And notice I haven't drawn arrowheads here because we know it's symmetric. So if 0 is related to 4, we know 4 is related to 0. So rather than drawing arrows everywhere in both directions, I'm just trying to draw an arc without an arrow, because we should assume that if we see this, then this is equivalent to this, or maybe I'll draw it like this, okay? An arrow in both directions. So 0, 4, and 8 form a little clique here. 1, 5, and 9 form another. 2, 6, and 10 form another. They're all congruent to each other modulo 4. And 3 and 7 form their own little clique. These little connected cliques are interesting, and we'll come to their definition in a moment. Similarly, if we have has the same parity as, then all the even numbers will form one blob and all the odd numbers will form another blob. So I've drawn that here. So we can see 0, 2, 4, 8, 6, 10. Don't know quite why I labeled them like that, but all of those are connected to each other. And 1, 3, 5, 9, and 7, all the odd numbers are connected to each other. And there's no connections between these cliques. Okay? Everything in here is connected to each other, but there's no connections between these cliques. So notice that all of these elements of A form into these little connected subsets, and these little connected subsets are called equivalence classes. These are somehow sets or subsets of objects that are all similar to each other and yet different from other connected subsets. So let's define that a bit more carefully. Let R be an equivalence relation on A, then the equivalence class of some given element, x, with respect to R, so we'll write it like this with square brackets around the x, is the set of elements in A that are equivalent to x. Okay? And remember, that relation has to be an equivalence relation. So in our congruent modulo 4 example, the congruence class, so that the equivalence class of 0 was 0, 4, and 8, and that's just the same as the equivalence classes of 4 and 8. Equivalence class of 2 is 2, 6, 10, and it's just the same as the equivalence classes of 6 and 10, and so forth. So these are our 4 equivalence classes that we get from congruence modulo 4. Now, one of the things that we can see is that no equivalence class is empty. So as a lemma, useful little lemma. If we take R to be an equivalence relation on a set A, then for any A is always in its own equivalence class. And this is just a technical result, it's kind of obvious, but it's useful to know that no equivalence class is empty. So proof of this, well, let R be an equivalence relation on A and pick out A from A. Since R is reflexive, we know that A are A, and so by definition of this equivalence class, back on the previous slide, which you can flip back to, A is in its set, or in its equivalence class, as required. So we know that every single equivalence class has at least one element. Now, let's think about equality of equivalence classes. Well, suppose R is an equivalence relation on A, and pick out two elements of A. Well then, the equivalence class of A is the same, is equal to the equivalence class of B, if and only if those elements are related. And we have to do this proof in both directions, so we have a bit of work to do to prove that result. So, first of all, we have to prove both directions. So let's start off with the left-hand side and show that it implies the right-hand side. Well, let's start by assuming that A, the equivalence class of A, is equal to the equivalence class of B, and show that A are B. Well, we know from the previous lemma that A is in this set on the left-hand side, because A is always in its equivalence class. Well, because these sets are equal, that means that A is in B as well. Because if A is in this side, it has to be in that side as well. Well, by the definition of B, the equivalence class of B, that's all the elements in A that are related to B. So if A is in that set, we have to have A are B. Okay, so that proves one implication. Going on to the other way, well, now we have to assume that A are B and show that that implies that these sets are equal. Now, of course, in order to show equality of sets, well, what do we have to do? We actually have to show that they're subsets of each other. So let's assume A are B and pluck out an element of this set and show that it's in the other set. So that's proving this inclusion. So let X be in the equivalence class of A, which tells us that X are A. Well, we know that R is transitive, so X are A and our assumption of A are B, transitivity tells us X are B. And by the definition of that equivalence class of B, we get X is in B. And so that proves that inclusion. Now the reverse inclusion, I won't do all the details here, it's very, very similar to that first inclusion, but we do need to use the symmetry of R to get B are A. Okay, so A are B, because R is symmetric, because it's an equivalence relation, that tells us B are A. And we need that little fact in order to make everything work. Okay. So now we can prove it. We need to prove each implication in turn. So we're just writing things up nicely. So let's do the inclusions to do the set equality first. So we assume A are B. So we're proving the reverse implication first. We assume A are B, and we prove that A is a subset of B and leave the other inclusion to the reader. So this is me telling you that in a formal way, hey, I'm going to do one half of this, you can do the other because it's similar enough and I don't have time to do it in this lecture. Okay, it's a little bit cheating, but we'll be okay. So we prove this and leave the other inclusion to the reader. It's a little bit naughty. So let X be in A. So we're going to pluck something out of this side. And that tells us by definition of this equivalence class that X are A. Now since R is transitive and A are B, we know X are B, which is exactly what we need to conclude that X is in that equivalence class of B, because that's the definition of the equivalence class of B. It's everything in our set that's equivalent to B. As required. So the other inclusion is similar, but uses the symmetry of R to do that one little extra step. So now, if we assume the other side, so we're proving the forward implication now, if the equivalence class of B is equal to the equivalence class of A, then from the lemma above, we know that A is in A, so A is in its equivalence class, and so A has to be in B because these two things are equal. So A is in the equivalence class of A, it must be in the equivalence class of B, by our assumption here. And then by the definition of the equivalence class of B, so maybe I should put in an extra word here, equivalence class of B, which is all the elements that are related to B, that tells us A are B, and we're done. Okay, let's stop there. You might find that you have to read through that proof, so we'll make sure that you have access to the slides for this. Okay, let's stop there.